So I'm here going to motivate the idea of the integral, which is the last of the major three topics in calculus, the first being the limit, the second being the derivative. So now we come to the third and final, which is the integral. So to motivate this, we're going to return to the idea of motion in one dimension. So we're moving along the x-axis in one dimension, and we have time as our independent variable. So time is ticking in the background, and we're keeping track of motion along the line here. Now, in this situation, we motivated the derivative, right? And the derivative mathematically tells you how to construct a speedometer, which would be the velocity at t, from the odometer. So the odometer here I'm interpreting as x of t, just position as a function of time, where you are on the line as a function of time, being your odometer. From that, you can calculate velocity. Right? This is just our definition of the derivative. Because the velocity is the derivative of position, we have the limit of the difference quotient as we've discussed. And our derivative is the limit as your time interval shrinks to zero of change in the position over change in the time. Now the integral is, in a sense, flips this situation around. So instead of constructing a speedometer from the odometer, what it does is it tells you how to construct the odometer, your x of t, from the speedometer, which is the velocity. So we'll explore a little bit more about what we mean by this. To explore what we mean by this, suppose I go on a trip along the x-axis. And I'm going to start here at the 10-mile mark. We'll measure in miles and hours for concreteness. So I start at the 10-mile mark, and I'm moving at 50 miles per hour, constant speed. So to get you to start thinking about the integral, I want you to think about the following question. So what is the odometer reading, x of t? So where am I on the line after a half hour in this situation? And you might want to pause and actually think about this. Well, since the velocity is constant, right, we're moving at 50 miles per hour, what that means is I'm moving 50 miles every 1 hour, right? But I'm only traveling for a half of an hour. So obviously the answer is that I covered a distance of 25 miles here. And that means starting at the 10-mile mark, I would have gone 10 plus 25 or 35, right? So I'd end up at the 35-mile mark over here. And all we did really was we took that 50 miles per hour, 50 miles over hours, times the 1/2 hour. So the hours here cancel, right? Hour, and then the 1/2 and the 50, right, becomes 25. So generally, it's the case when velocity is constant. Right? Your distance covered, that's the 25 miles up here, what you would do is take your velocity, which is miles per hour, and multiply by the hours. Right? So in other words, you would take your velocity and multiply by time, and that would give you distance covered. Right? And this all checks out because velocity is distance divided by time, right? Distance over time. And so velocity times time, the time here, canceling the time in the denominator and leaving just the distance. Right? So this is the situation when velocity is constant. But if velocity is not constant, then things aren't so simple, right? So if velocity is not constant, you can imagine the trip in your one dimension. You can imagine starting slow, maybe speeding up, slowing down again, speeding up. Then there's no one single number that's going to encapsulate this velocity here, right? There's a multitude of velocities at different times. And so just taking the time elapsed and multiplying by velocity, well, there's no representative velocity, there's no number here sort of encapsulating all of the velocities that you're encountering along your journey. So you can't calculate distance covered using this formula anymore because there's not a single number involved. So what do? How do we get distance covered, right? How do we reconstruct our odometer, which is telling us how much distance we're covering, from the velocity, if the velocity is variable? Well, here's what we do. So let's say that on my journey, I start at time A. Okay, so there's a lot going on here. I'll walk you through it. So we start at time A, okay, where I'm here. We're going to end at time B, where I'm over here. What we do is take that time interval and divide it up into a bunch of smaller time intervals. Okay, so in this picture here, I've taken my interval of time from A to B, and I've divided it up evenly into 7 pieces. Okay, so I have 1, 2, 3, 4, 5, 6, 7 pieces here. So I've taken A minus B, or B minus A, and I've divided it by 7. That's these little time intervals, delta t here. And now my velocity might be varying as I throughout this time interval, right? So the velocity in this small time interval here might be large, so I might span this distance, whereas the velocity in this time interval over here might be small, so I might span a smaller distance. Okay, so the time intervals here are evenly spaced, even though it doesn't look like that. So I'm showing the spatial separation here. That might vary even though the time intervals themselves are the same amount. Okay, so I might cover more distance in the same time, depending on the velocity. Now, the key thing is that in these little windows here, right, in this small time interval here from, say, t0 to t1, the velocity will be approximately constant, or at least it'll be more approximately constant than it was over the full time interval. Right, if I look in this small little time interval here, approximately the velocity will be constant. It might be varying, but it's going to vary a lot less in here than it did over the whole time interval. So the basic idea then is that what we're going to do is apply the distance equals velocity times time formula, which works when velocity is constant on these small time intervals of size delta t. So the basic idea is that since velocity is approximately going to be constant throughout this interval here, I can just take any time between, say, t0 and t1, look at the velocity there, and then if I do that velocity times time, that will approximately be the distance that's spanned in this time interval here. Okay? So again, the situation is this. I have this longer journey where my velocity has ups and downs, not so constant. I divide that into smaller journeys, right, of the same time. So I look at this smaller journey here, this smaller journey here, this smaller journey here, and in each of those journeys, the velocity is basically constant. It's a lot more uniform than it was over the full time interval. So then I just pick a time in here, look at the velocity, and let that sort of represent all of the velocities in this time interval. So roughly then, the velocity when our little person is here, if we multiply that velocity by the change in the time here, that will roughly tell us the distance that was covered in this time span. Okay, so what that leads us to is the following. So we can estimate the distance covered because we now have an estimate for the distance covered in each of these small time intervals. And in this small time interval, we can pick a time, look at the velocity, and estimate the distance covered in that small time interval, and do that for each of these intervals. And that will give us an estimate of the distance covered on each of those small time intervals, and then we just add them up. So the distance covered, if I denote, so I'll denote T1 star, that will be, I'll just pick a random time between T0 and T1 and look at the velocity there. So I'm using this velocity. I want to multiply that by the time that elapsed in this part of the journey. So that's T1 minus T0, which is going to equal this delta T. So I have velocity times time, right? That's equal to distance, where it's going to approximately equal the distance covered in that part of the journey. Then I do the same thing here. I pick some time T2 star between T1 and T2 to look at the velocity at. Okay, so look at the velocity here, multiply that by the time elapsed, that will approximately tell me the distance in there. And I just go along and I do that for every single one of these little windows of time. Okay, so velocity times time, velocity times time. I add them all up. And what I find Well, my time intervals, they were all delta t. So I just have these velocity at the t1 star times delta t plus etc. Velocity at t7 star times delta t. And I can write that compactly using what's called sigma notation. So this here, I just have a sum over all of those times in those little time intervals, right? So I had 7 time intervals, 1, 2, 3, 4, 5, 6, 7. And in each of them, I'm looking at the velocity at that particular time times the length of the time interval. Right? And I'm just adding those up. So that's what this sigma means here. The sum going from 1 to 7. So summing from the first time interval up through the 7th. It's the same thing, velocity times time in each of them. So then from there, what we want to do is, that was just an estimate of the distance covered. So we want to get a better estimate. Right? So we can get a better estimate by dividing up the time interval into more pieces that are smaller. Okay, so if we divide our time interval, right, the time of my trip, into n pieces, where n now might be bigger than 7. So before it was 7, maybe now it's 100. So I divide it into n pieces. The size of those pieces is going to be a lot smaller, right? But I'll still denote it by delta t. And then in each of those time intervals of size delta t, I look at the velocity at some time. Right? So I pick a time in that time interval. Throughout the time interval, the velocity is going to be basically constant. So this velocity that I choose at a particular time is going to represent pretty well the velocity throughout that time interval. Then I do velocity times time there. That gives me the distance, approximately, gives me the distance that is covered in this little time interval. And then I just add that up over all of the time intervals. Right? So we estimate the distance covered in small time intervals. That's what each one of these little parts of the sum means. And then we just add that all up. So given that the estimate is getting better and better as we divide the time interval more and more, right? So as we divide this time interval into smaller and smaller bits, our estimate is getting better because our velocity, right, when we choose a velocity here, the velocity is more and more constant over these smaller and smaller time intervals. Right? It varies less and less. So these approximate distances in the small time intervals are getting more and more accurate. And so what we can do is just allow this number of times, number of divisions of our time interval into n pieces to become larger and larger. So we're going to keep breaking up our journey into more and smaller pieces. Okay, so that's this. So what we're going to do is take the limit of this sum here as n goes to infinity. So what this is sometimes called a Riemann sum. And then once you take the limit of such a sum as n goes to infinity, that is called the definite integral of this function v, right, our velocity function. So this is the definite integral of our velocity function from the time a to the time b. Right? This is where our journey started, the time at which our journey started, and this is the time at which our journey is ended. So if we do this process, which is called the definite integral, so if we take the definite integral of our velocity, then that tells us the distance covered. Okay, so the basic idea is really rather simple. The idea is that distance is velocity times time as long as our velocity is constant. And when your velocity is not constant, you estimate. You break up your time interval into a bunch of smaller time intervals so that the velocity is basically constant. And then you can apply the velocity times time equals distance. And so you estimate the distance covered over small time intervals, and you add up all of those distances to get an estimate of the distance, the full distance covered. And then to get rid of the estimate, to get an exact answer, you take the limit as the number of subdivisions becomes larger and larger so that your approximation becomes better and better. The velocity becomes more and more constant over those very tiny time intervals. And in the limit, you recover the full distance that was covered on the journey. And that's called the definite integral. So in the next video, what we're going to do is develop geometric interpretations of all of the terms in these formulas. Okay, so we'll develop a geometric interpretation of this Riemann sum here, and then a geometric interpretation of what the limit is, very similar to what we did with the derivative. Okay, so more on that later.